Now we're going to look at the ways we describe the masses of elements, moles of elements, and ionic compounds. We're going to start with atomic mass. Atomic mass is the mass of an atom of an element in atomic mass units. AMU is the abbreviation for atomic mass units, and these masses are compared to a carbon-12 atom. So C12 has been assigned an atomic mass that is exactly 12 AMUs. And all the other masses on the periodic table then are relative to that carbon atom. So we can also say then that let me turn my pencil on, one AMU is equal to 1/12 the mass of a carbon atom. Also shown on this slide are the masses of both hydrogen and oxygen using this scale in AMUs. So we do know, however, that elements can exist as isotopes. And those isotopes, or the abundance of those isotopes, varies in nature and depending upon what that element is. We're going to take a look at lithium. It has two isotopes, L6 and L7. We're given their masses in atomic mass units and their percent abundance in nature. And we'll talk about how that's determined in a little bit. But the way this is calculated is by taking the percent, and this is the way your book does it. I'm going to show you a different approach, and multiplying the percent abundance times the mass of that particular isotope. And if there are more than two, then you would sum all of the calculations for that particular number of isotopes, and then divide by 100. So really a working definition of atomic mass is the average atomic mass for naturally occurring isotopes of an element expressed in atomic mass units. And the average atomic mass of lithium then is 6.941 AMUs. So here's the periodic table of elements. And I want to point out, if we look at lithium, 6.941. So the atomic masses shown on the periodic table are actually the average atomic masses. This is just an aside. In some textbooks, not yours that I'm aware of, 1 AMU is equal to 1 Dalton. That's more, that unit is more often used in biology than chemistry. And we're going to also take a look at the technology that allows us to determine the masses of and the percent abundance of those particular isotopes of an element that are found in nature. And that technology, oh, I'm sorry, I didn't put that little average thing. That technology is an instrument called a mass spectrometer. And this is a schematic kind of diagram of what that looks like. But in this example, a gaseous sample, as you can see here, is injected into the instrument, and then it's bombarded by a stream of high energy electrons in this region. So these are the electronic beams. And this transforms the gas molecules into ionized fragments. and they're positive ions. These positive ions are then accelerated through a mass analyzer to the detecting screen at the end. And the masses are then determined by the degree of deflection. And you can see that some of these particles or ions hit the screen here and some over here. The lighter charged particles hit the screen on this end, heavier ones toward the right. And then the detecting screen enables the determination of the relative abundance of those isotopes. So if you look at the graph down here, you'll see some peaks. So this is the analysis from the data that's gathered by the spectrometer. And this tall peak represents that light or lighter isotope. And that is, I think this is for neon, I do believe. Yeah, that is neon 20. You'll see a very small blip here, that's neon 21. There's a little bigger one here, that's neon 22. So neon has 3 isotopes. But we're going to walk through an example of determining, based on mass spec data, given by the percent abundance and the mass of those isotopes, how we calculate the average atomic mass in just a slightly different way. And there's here are the heavy ions and the heavier peaks corresponding below. Okay, so to calculate the atomic mass from mass spec data, we need to know, number one, the relative atomic mass of each isotope. Of course, these are naturally occurring isotopes, and the percent abundance. Or fractional abundance. And that's what my method uses. And basically, that is just converting that percent to a decimal to do the calculation, okay? And a generic setup then for calculating average atomic mass equals the atomic mass of some element 1 times its fractional abundance, or decimal, plus the atomic mass of isotope 2 times its fractional abundance, and on and on. Depends on how many isotopes of a particular element exist. So we're going to use mass spec data to calculate the average atomic mass of neon. And we just saw that neon has 3 isotopes. Sorry, I forgot to turn that camera off. You see, my hand was interfering. And these isotopes have masses of 19.99 AMU, 20.99 AMU, and 21 20.99 AMU. And their corresponding natural abundances are 90.51%, 0.27%, and 9.22%. So all this information came from that mass spectrometry analysis. So I convert these to decimals prior to setting up the calculation. We're also going to talk about sig figs in this calculation. So I take my decimal 0.9051 times the atomic mass of that isotope in AMUs plus 0.0027 times 20.99 AMUs. And I'm writing too, my writing's too big, so I have to put this one down here. And then we have 0.0922 times 21.99 AMUs. Units. Remember, numbers mean nothing in chemistry unless they have units associated with them. Okay, so to work this and think about sig figs at the same time, we have a mixed math problem here. We have multiplication and we have addition. And we're going to perform the multiplication steps first. And when I do that, I get 18.092 AMUs here. And I'm going to mark the number of sig figs that are allowed in this answer. But I'm not going to round it yet. No rounding ever till the final step in your calculation. So I look at my original numbers, and I have 4 sig figs here and 4 here. So I need 4, or I'm limited to 4 in this number. And that's going to make a difference in the next step, because the next step is addition, and we will have to follow the rules of sig figs for adding and subtracting. So I'm going to go ahead and do the next multiplication. This gives me 0.056673 AMUs. And I have 2 sig figs here and 4 here. So I'm limited to 2 significant figures in this number. And then the last product is 2.027478, and again, AMUs. That's a 2. I have 3 sig figs here and 4 here, so I'm limited to 3 in this product. Now I'm going to add all 3 of these results together using all the numbers, or most of the numbers. I think I left a few out, but I gave 4 decimal places here. So 20.1761 AMUs. Now I have to follow the rules for adding and subtracting with respect to determining the sig figs in my final answer. And that is based on the least number of decimal places. This has 2 decimal places, this has 3, this has 2. So I'm permitted 2 decimal places in my final answer. So final answer is 20.18 atomic mass units. So please remember, sig figs matter. You will lose points if you don't give the correct number of sig figs. Now, before we talk about the next mass, we are going to talk about the mole, or the chemist dozen. So we are used to describing, or we have words to describe numbers. And we know what a dozen eggs is. A dozen equals 12 eggs. A baker's dozen equals 13. But if we have a pair of tennis shoes, we know that means 2. We have 2 feet. Shoes come in pairs. So the mole is the amount of a substance that contains as many units as there are atoms in exactly 12.00 grams of C12. And this mole unit can be applied to anything. We'll only use it with respect to atoms and molecules, but we could talk about a mole of basketballs, or a mole of pennies, or a mole of apples. It's just a number. And that number is called, I'm sure you've heard of it, Avogadro's number. Oh, let me just push this here and erase what I started to write. So this is the abbreviation for Avogadro's number, N sub A, and 1 mole contains this many things. And again, doesn't matter if it's marbles or eggs. It contains 6.022, 1.367 times 10 to the 23rd units, or pieces. We are not going to use all those numbers. We are going to limit our use to 6.022 times 10 to the 23rd. Just know that, or keep in mind that you will not use Avogadro's number to determine sig figs. So now that we've introduced the mole, we can talk about molar mass. And molar mass is the mass of 1 mole of whatever we are talking about. Again, if we have a mole of eggs, there's going to be a mass associated with that. If we weighed them. If we have a mole of shoes, that would have a certain mass. A mole of marbles, a mole of atoms, a mole of molecules. They all have the same number of pieces, but they will have different masses. So, this is easy, or this one's easy. 1 mole of C12 atoms equals Avogadro's number of atoms, and it also equals, or it has a mass of 12.00 grams. 1 single carbon atom has a mass of 12.00 AMUs. So what that means is that we take the same value, and these are examples coming up here, for any element, the value, or the numerical mass in AMUs on the periodic table is equal to the same number with units of grams. So the molar mass is just the same numerical value of the atomic mass, but we change the units to grams. Okay? So that means that molar mass has units of grams per mole. And that will come in handy later when we start doing some other dimensional analysis type problems. So what is molecular mass? Molecular mass is going to be the mass of one molecule or compound. So it's the sum of the atomic masses in AMUs of those atoms in the molecule. So this is a compound, as I said. They're using it as an example here, SO2. We see that we have a sulfur atom and 2 oxygen atoms. So in order to calculate the molecular mass in AMUs again, we find sulfur's molecular mass, or average atomic mass, in AMUs on the periodic table, and add to that 2 times the mass of an oxygen atom in AMUs. And the sum of that will give us the molecular mass in AMUs. What's the molar mass for that molecule, or a mole of those molecules? Same scenario here. We just changed the unit from AMUs to grams. So the molecular mass of one molecule of SO2 is 64.07 AMUs, and a mole, or Avogadro's number, of SO2 molecules has a mass of 64.07 grams. So the only difference, again, is the unit. The numerical value is the same. And then finally, we take a look at ionic compounds. And ionic compounds, as we know, are not covalently bonded molecules, and they arise from a strong electrostatic attraction between those positive and negative ions. And the basic unit of an ionic compound is called a formula unit. Okay? So formula mass, then, is the sum of the atomic masses in AMUs in a formula unit of an ionic compound. So molecules have molecular formulas. Ionic compounds have formula units and formula mass. And this would be molecular mass. Difference in terminology. So pay attention. But they're calculated the same way. One formula unit of sodium chloride, oops, sorry, let me erase that. Is calculated the same way we would calculate the molecular mass. We're going to look up or find the atomic mass on the periodic table for sodium and for chlorine, add those together. So one formula unit of sodium chloride has a formula mass of 58.44 AMUs, and 1 mole of sodium chloride has a molar mass of 58.44 grams. Okay? And so that ends our discussion of the masses, and we will move on